Okay, we saw that one way of measuring changes in capacitance is by using AC voltage dividers. Let's look at a few more ways, and in this video we're going to look specifically at measuring changes in capacitance. Okay, one of the scenarios that you could have with capacitive sensors is that the physical quantity actually uh, changes basically the distance between the two capacitive plates. Okay, let's assume that you're measuring x is the displacement between the two sensors and the capacitive plates are moving apart and coming together. Okay, in that case x is going to be inversely proportional to the capacitance. Now if this is the case, what you want to do is you want to put this capacitor in the feedback here. Now, if you do that, what you would find is the output is going to be linearly proportional to x. And this happens because the impedance Zx is actually inversely proportional to Cx, right? You have a 1 over j omega Cx. And because of that, now x is, again, Cx is has a 1 over 1 plus x influence, and therefore x then comes in the numerator, and then x becomes directly proportional to the output voltage. Okay. uh, Now we've not really accounted for this r in our equations, and let's just assume that this r is large enough so that we can ignore it. You need this resistance basically because you want to give a discharge path for this capacitance, but let's just assume that R is not really important in our circuit. Well, you may ask, why do you need a discharge path for the capacitor? One reason is because even though we assume that there is no current flowing into the input of the op amp, there is a small current flowing, as we have already looked at before. And if there is a small current flowing here, where is that current going to come from? Let's say that's a DC current. Where is that current going to come from? It cannot come from this capacitor. It cannot come from this capacitor because these are basically they block DC voltages. So it has to come through some way, and what we are saying is it comes through this resistor. Okay. Uh, Now, what happens if the displacement or the physical quantity is directly proportional to the capacitance? You could have sensors where the area between the two plates varies, or the permittivity varies by some means. So then you will have the capacitance which is directly proportional to x. So if you want to measure this kind of a quantity, what you do is you put the sensor in the input side, not on the feedback. Okay, and if you do that, you can again see that what you would get is an output that is proportional to x. Now note that in both the circuits, this circuit and the previous circuit, the input voltage is an AC voltage. Now that is very common in all reactive sensors. You need to have an AC voltage. Okay, why is that? I'll leave you to think about it. Okay, now the measurement of capacitance is always um, complicated by the fact that you have parasitic capacitances. So if you have two wires in a circuit parallel to each other, they have a capacitance in between them. You can think of them as a plate, right? A very, very thin plate, but plate nevertheless, and they have a distance. So there's a capacitance between them. That's a parasitic capacitance, and that would give rise to parasitic capacitors all around the sensor that we are using. Now that's a problem, right? You don't want these capacitors to influence the measurement of this capacitance, because if your measurement of this capacitance is wrong, then your x is going to be wrong as well. So what can you do? Now, luckily, the way this circuit is constructed, CS2 doesn't influence the measurement at all. Why not? Because one side of CS2 is connected to ground, and what is the voltage at this side? So the voltage at this side is the same as the voltage here. And what's the voltage here going to be at the inverting input? It's going to be the same as the non-inverting input, which is equal to ground. So it's ground on this side, ground this side, so 0 volts, 0 volts. So no current is going to flow through it. So it's as if this capacitance is not really important. We can just remove it from the circuit and from our analysis. What happens with this CS1? So Yes, when some current flows out of this source, it can go through CS1 or it can go through CX, right? But whatever current goes through CX actually flows through this capacitor and therefore contributes to the output. The current that flows through CS1 can basically be ignored because it doesn't matter whatever it is, as long as it is a constant and it does not kind of vary during the measurement, we can ignore it. Because if a fraction of the current flowing here comes through this, that fraction is going to flow through C, and therefore you will get an output because of that current. So the current flowing through CS1 you can ignore, and therefore you can ignore CS1 and you can ignore CS2. You can't ignore CS3, right? Because it's in parallel to CX, and whatever measurement you're going to measure the combined capacitance of CX and CS3. So how are you going to reduce CS3? One way to reduce it would be to shield your sensor and to make sure that the layout of your circuit is such that this parasitic capacitance is reduced.